Okay, so we're going to look at this example here. Um, we have a Y to Y connection here, so a pretty straightforward thing to look at here. But the problem gives me that this is the load here. So instead of drawing that multiple times, we draw ZP. It's balanced load still, which is good, but this is my load for each of those things. So one of the things we're going to have to do is we're going to have to compute ZP. Now, one thing that we didn't talk too much about yet is what we are given here. This is VAB. So VAB is what we refer to as a line voltage. And we call it a line voltage because we're measuring a voltage from two lines, a line to a line, as opposed from a line to a neutral. So we call that a line voltage, a line-to-line voltage. Now, if we're wanting to see this here, one thing that we should know here, and we could go through the reasoning behind this and look at phasor diagrams, but I don't think that provides a lot of insight here. There's three equations that we want to kind of star here for ourselves. Is if we're talking about line-to-line voltage, VAB is simply equal to the square root of 3 of VP at an angle of 30 degrees. So remember, we have here, if we're assuming, and if we're not specified otherwise, you can always assume a positive cycle, an ABC phase cycle for this. So, you know, this would be VP at an angle of 0 degrees. This would be VP at an angle of, well, instead of saying 0 degrees, I'm going to, well, yeah, 0 degrees, VP at an angle of negative 120, VP at an angle of negative 240 degrees. Now, that's because we typically assume that this is 0 degrees. Because my line voltage is at 0 degrees, we're actually going to get something different for this. But I'm just representing that here so that we can see, oh, VP here, I can correspond these VPs together. Okay? So, if I want to think about this here, if I'm looking at VAB, it's the square root of 3 VP at an angle of 30 degrees. VBC, because there's three possible combinations, it's going to be VP square root of 3, and then this is going to be an angle of negative 90 degrees, and then VCA is equal to the square root of 3 VP at an angle of negative 210 degrees. Now, if we use this information, we can actually find our value for VP, because what we can do here is, if we want to think about this, if we think about VP then is like the source we want to find, we could rearrange this equation and just think of this as VP would be VAB divided by the square root of 3 at an angle of negative 30 degrees. Because if I divide by an angle of 30 degrees, I just get a negative 30. I get a subtraction there. But then if I have VAN is VP at an angle of 0 degrees, then this would be VAB over the square root of 3 at an angle of negative 30 degrees kind of at an angle of 0 degrees. And what do we do here is, well, basically these angles, because they're getting multiplied, get basically added together. So VAN would just be VAB over the square root of 3 at an angle of negative 30 degrees. Now, similarly, you could do this same thing if you wanted to find like VBN and VBC, VCN, but actually what we do is we'll find VAN, and then we can get all of the other ones, even though the problem only asks us for VAN. So these are some important equations here. So I'm going to go ahead and scroll down here just so that I don't have to erase things. So what we have here is we have VAB is 400 at an angle of 0 degrees. So we have VP would be 400 and an angle of 0 degrees divided by the square root of 3 and an angle of negative 30 degrees. So VP, 400 divided by the square root of 3. Whoops, I did multiplying there. That does not work. $231 volt. And we're assuming we're in RMS as well. I should maybe state that here. I didn't state that. This is volt RMS. So here we have volt RMS. At an angle, actually, we typically write the angle first here, at an angle of negative 30 degrees. Volt RMS. Great. So we have VP, but then again, using my formula here, VAN then is simply going to be 231 at an angle of negative 30 degrees. Volt RMS. So if I go back to my diagram here, this is now 231 at an angle of negative 30 degrees. Now that's all it asked for in this problem, was to find that it was 231 at an angle of negative 30 degrees. But we have other things we could do here. For instance, VBN would just be, well, it's still going to be 231 at an angle, and what we do is, well, there's an angle difference of 120. So this would be minus 150 degrees. And then this one would be volt RMS. And then this one would be another 231 at an angle. Take another 120 away, minus 270 degrees, VRMS. So that's why you only really need to find VAN from a line voltage. And the reality is you can kind of be given any of the line voltages in order to figure out what VAN is using these formulas right here. And then once you have VAN, you get the others just by doing a phase shift. Okay, now it asks for what IAA was, and it wants to know what the total power drawn by the load is. So that's the current going through here. And so simple Ohm's law, because I'm in RMS here, whoops, simple Ohm's law tells me that IAA would be equal to VAN divided by the impedance ZP. But I need to know what ZP is. That's why we have this circuit here. Now what we can see is these three kind of components here. Now when I say three, I'm kind of combining these two in a single component. These two are in series, but these three are in parallel here. So if I want to think about what ZP would be, it'd be 1 over negative J100 plus 1 over 100 plus 1 over 50 plus J50, and then that whole thing to the negative 1 power. So I'm going to pause the video here recording while I compute that. And when I did the computations, I wound up with a 25 plus J25 ohm load. So then my current, actually what I'm going to do here, I'm going to go ahead and convert this to polar since I'm doing division here. So converting this to polar, I get 35.36 at an angle of 45 degrees ohms. So my current IAA would be my voltage, which is 231 at an angle of negative 30 degrees, volt RMS, divided by 35.36 at an angle of 45 degrees. And I apologize here. I am going to actually erase this, because you may have, when you're done your computation, got a different value. This is why you need to be careful with your computations. When I did my computations, I forgot to include this negative here. Very critical there. And if you include that negative, you don't get the 25 plus J25. You wind up getting just simply 50 plus J0 ohms, which is just 50 ohms. And if you want to think about it, it's 50 ohms at an angle of 0 degrees. So we still compute IAA as the same way here. And I like it in polar format, because what would we have here? We'd have 231 at an angle of negative 30 degrees. And I'm still going to write this as an angle of 0 degrees just to illustrate a point here, divided by 50 at an angle of 0 degrees. So 231 divided by 50 would be 4.62, and this would be at an angle of negative 30 degrees minus 0 degrees, which of course is still negative 30 degrees. But the reason I emphasize it is if you got your load to be something like 50 plus J10, or like I did 25 plus J25, you know, we have an additional angle in there that we'd be subtracting off after we do our division. Okay, but we don't have that, and so this is simply 4.62 at an angle of negative 30 degrees amp RMS. So now we want to know what the total power drawn by the load is. Well, if we think about the ZP, and I'll put here the A connection, we know the voltage across that. We know that that one, and actually I'll just go ahead and do ZAP to indicate that. We know that the voltage drop across it is just VAN, which is 231 at an angle of negative 30 degrees, volt RMS. And we also know that the current going through that is 4.62 at an angle of negative 30 degrees amp RMS. And we also know here that then my power, complex power, is equal to, well, in this case it's going to be just my voltage times my current, because there's no 1/2 because I'm in RMS. So what we end up getting here is the power for the AZP would be 231 at an angle of negative 30 degrees times 4.62 at an angle of negative 30 degrees. So if I multiply this out, I'm going to go ahead and write the whole thing out here, including the decimal. 1067 at an angle of negative 30 degrees. Now I'm going to convert that to rectangular format here. I'm sorry, this shouldn't be negative 30, it should be negative 60, because you add these angles. And I made a mistake here. I apologize. I'm making too many mistakes right now. I made a critical error here. Some of you probably caught it. Power is not voltage times current. It's voltage times the complex conjugate of the current. something just wasn't working right in my head. I'm like, something's going on wrong here. I'm doing something wrong. So in this case, then it would be 231 times 4.62. Now to do the conjugate of the angle here, we have to be a little bit careful here what the conjugate would be, but it turns out the conjugate would just simply be getting a positive, a 180 degree phase shift, I believe. It would just be at the opposite angle. So it'd be plus 30 degrees. So we actually get the same number here because we still have 4.62 times 231. So we still get 1067, but the angle now is at 0 degrees because I'm adding those together. So, and this is actually not P, this is S because it's complex power. But that would just be 1067 plus J0 for S. So that means as far as the average power goes, we're getting 1067 watts on the load there. But that's not actually the total power delivered. Because that's only one of the loads, and we have 3 loads. So each load draws 1067 watts. So if I times that by 3, we get that the total power drawn is 3200 watts or 3.2 kilowatts. Alright, so this video here was again just kind of go back and summarize what we were doing here is we were going through, and you can see, analyzing a three-phase circuit is really not as complex as it seems like to be. Maybe I made it complex with my discussion, but let's go back through and see how easy it is really. Okay, so we're given a line voltage, so we have a set of equations to given a line voltage that we can compute VAN. And we have it here. If we wanted to do it for the VBC here, VAN, if you were given, here I'll just write them beneath here in blue. So if you were given VBC, VAN would be VBC over the square root of 3 at an angle of 90 degrees. And VAN would be VCA over square root of 3 at an angle 210 degrees. So if you're given a line voltage, it's easy to figure out VAN. And then once you know what VAN is, to find VBN and VCN, you're literally just adding a phase shift. And now we're going to be examining just the balanced load situations here. So when we have a balanced load, what's nice about that is we simply just go ahead and, we just have the same voltage drop across each of these loads. And what we had to do here is, given this load, we had to compute ZP. So that's where we did this. Computed ZP, got it to be 50 ohms. Computed the current then, IAA, just by doing voltage divided by current, voltage divided by impedance. And then remembering the correct way for the power, its complex power is voltage times the complex conjugate of the current, which means I have the voltage here. The complex conjugate of the current basically just makes this a positive 30-degree angle, which gives us the following result for our complex power, which means that the actual, if we want to talk about the number of watts, the actual average power that the load is absorbing was 1067. But remember, when we did those computations, that was just the average power being absorbed by this load. But since we're in a balanced situation here, all three of these loads are going to absorb the same amount of power. You don't have to do the phase angle shift, because the phase angle shift just means it's at a different quote time, so it's not a really big deal. And so we would have the same power being absorbed by each of those loads, so we get to simply just multiply this number we found by 3. And we get 3,200 watts, or 3.2 kilowatts. All right?